All right, Zoom's got this like new AI Zoom recording companion. I don't know what that means, so we'll see. We'll see what it ends up being. I think it's like it's gonna like break the video into chapters of some sort. I'm not sure. We'll see. Okay. So what do you think? What do you think the parametric surface of, you're going to want to get together with your classmates to brainstorm this one, if you need to, of this vector function with uv, where x is given in terms of u, y is given as u squared plus v squared, and z is given as b. So what do you think this surface looks like from our discussions last week? Let's see. Have you guys here checking with each other? Anything for you? You guys check in here. Actually, you two check in, and then I'll have you three come back. Okay? As usual. Thomas and Sam, you guys can check in with each other. You three here check in with each other. And would you mind if you just have a seat on this side so you can check in with Dylan? Thank you. Oops, too much. Okay. I'm going to pass back some homework. You guys are chatting with your classmates. This is yours, right? All right, guys, check with your classmates. Put your heads together. Huh? Oh, that's your homework. Oh, it's two different ones. You can still submit it, it'll just be counted. Yeah, it's still counted. Okay, guys. All right, let me hear from, let me go like this. Any ideas what this looks like?
I think it will look like a paraboloid,
Okay.
because you can get the equation x squared plus z squared equals y.
X squared plus z squared is, okay, so walk me through how you got this here. You're correct, by the way.
I just look at the coordinates, like u squared plus v squared.
Okay. So that's this guy and that's this guy. Okay.
Yeah, I thought x squared plus z squared is the same as y.
Gotcha. Okay. So y is equal to this, but x equals u and z equals v. Okay, cool. And so then you're saying that that gave you a paraboloid. This bad boy here. This gives you a paraboloid. Do you remember which way it was facing?
See the plus y direction.
In the y direction. Well, what do you guys think? Yeah? Yeah, so we got this nice paraboloid going this way. Opening in that direction. Good. That's right. And so that's what we were discussing on Tuesday last week, is a different way. We've been graphing a paraboloid, this paraboloid, for example, with this equation. But now we can we can also graph it using what's called a vector function and parametrizing that surface. Okay? So we're going to use that. That's what we were discussing last week. Thank you, Kevin. And so we're going to continue that. So you might need your packet with all the pictures on it today. We're going to have a lot of visuals today, especially 16.7. So we're going to talk about tangent plane and surface area. Big title of parametric surfaces. Big old title. Woo. So let's start with this part here that we discussed. So last class, we learned how to parameterize a surface S using a vector function, like the one from the warm-up, and it used two coordinates. That's where we left off. And what we discussed was, for example, anyway, we saw here through Kevin's explanation how we get a paraboloid here. Remember that this paraboloid, we were thinking of this parameterization as like a grid of longitude and latitude lines, right? So for example, if we fix one of the u's, let's say I let u equal 1. Okay, if you let u equal 1, then this vector function is going to become 1 plus v squared and v, like that. And so notice, if we kind of go off of what Kevin was mentioning, we're going to have that y is equal to 1 plus v squared, if v is equal to z. So we end up with 1 plus 1, y equals 1 plus z squared, where x is equal to 1. Okay? What is on the yz plane? What does this look like here? Just on the yz plane, though. On the yz plane, it won't be a surface. It'll be a curve on the yz plane. and it'll be
Parabola shifted up one, opening towards the possible y-axis.
a parabola shifted up one towards the y-axis, right? Where x is equal to 1. So notice that where x is equal to 1, you're going to have a parabola that got shifted 1 unit up like this. Okay? So what's happening is for every u that I fix, if I let u be a different number, I'm going to get a different parabola. If I let u get bigger, it's just going to give me a bunch of parabolas like that. Okay? If instead I would have fixed v to be 1, I would have gotten u1, and I would have gotten u1 plus u squared, comma 1. See that? So now y would have equaled 1 plus u squared, but u is x, where z is equal to 1 now, because we're letting v equal 1, which is really z. So that means that when z is up 1, you're going to get a parabola that's shifting up 1 in the y direction. So you're going to be getting, you use a different color, you're going to be getting this parabola like this. Like that. You guys see that parabola? And you're going to get more of those, right? So it's kind of like what you guys learned earlier in the semester, level curves and all that. It's kind of what's happening. But for each u that I fix and I vary v, I get these lines, these parabolic curves. And if I do the same thing to v, I get different parabolic curves. And so your surface kind of becomes a collection of all these curves together that make up the surface overall, okay? And so that's kind of how we created these parametric surfaces, was with this vector function. And so there's this point, and then the other one is, we saw that when we fix, when we fix either u or v, we end up getting, and the textbook doesn't use this, but I'm calling them the longitude and latitude curves of the surface. And you could do that same argument kind of the way we were discussing this here with every single one of these surfaces. The curves that you get are the ones that could vary. Okay. Okay. So this is what we're going to do now. So we're going to go off of this. We're going to start this off with a general surface. Okay. So let S be given by some vector function. This is now a general surface. So here's X, Y, and Z. And let's say you have, dang it, this green one always falls on me. Let's say you get this surface here. Here's S. For some fixed u, let's say u equals u naught, we get curve Cu on S. Let's say that it's this curve like this. This is curve Cu. Kind of the way when we let u equal 1, we got the parabola. Okay. Yeah, so that CU curve is like the parabola that we had here when we let U equal 1. And then we're going to do the same thing, but now for V. So for some fixed V equal V naught, we get curve CV on S. That one, let's see, I already used green. My orange marker just doesn't want to behave with me. Yeah, I'll just get the black. Bless you. So let's say we get this curve like this. This is curve CV. Notice they're going to intersect in this case. They intersected at some point we're going to call P. Okay? What values of U, what would I have to plug, which U do I plug in and which V do I plug in to R to give me this point? What do you guys think? So pretend that U equals 1, that's like this guy, and pretend V equals 1, that's like this one. What would I have to plug into R to give me point P? You'd have to plug in 1, 1, right? Because this point lies on the curve CU where U is equal to U naught, but that point also lies on the black curve where V is equal to V naught. So if I plug in U naught and V naught into R, that's going to output the vector giving me P. Okay? And so at P, we have, sorry. The two curves intersect at point P where we plug in U naught and V naught into V. So for example, what do I get when we plug in 1, 1 into this guy here? We'll plug in 1, 1, I'm going to get the vector 1, 2, 1, which has a terminal point 1, 2, 1. And that point, 1, 2, 1, is the point intersected by the curve of what we got for this guy here, this first one here, and then the first one on top. It would be this point right here. And that's kind of what that's saying. So this green one right here was for U1, and then this first black one here, that's for V1. Where they intersect is at that point. That's what this is saying. Okay. So notice there's a point on the surface. I want to figure out how to find its tangent plane. If there's a plane that's tangent to the surface at that point, how do I find that tangent plane? Okay. Any ideas before I just tell you how to do it? What do you guys think?
So we would do with partial derivatives.
There are partial derivatives involved, and there are inputs and outputs. Correct. For a plane, we need a normal vector, right? Okay, so we need a normal vector. So we're going to want a vector that's completely perpendicular to the surface. We are going to need a cross product, good. But the cross product of what? What do you guys think? Two what? Two vectors that are tangent to the surface. So if we can find two vectors that are tangent to the surface at P, we take the cross product and that'll give me a normal vector. And then I have the point, because remember for a tangent plane, you need a normal vector and a point. I have the point, I need to find the normal vector. Beautiful, good job. Okay, which tangent vectors do you think we can find?
I'm fine.
You guys see here how when we would let u equal 1, we got this vector function here. Think of this vector function as like what you guys did in chapter 13, if I gave you something like this. Yeah, remember that? And how did you find tangent vectors with it? I'm asking you guys because the finals next week, so that's why I'm doing it, okay? So be patient. You took the derivative, exactly. But here you have the derivative of one variable. In this case, you have two variables. So that's where Jacob's comment of partials comes in. Beautiful, good job, guys. Okay, that's exactly what we're going to want to do. We're going to want a tangent vector. Let's say the curve is oriented this way, and let's say the black curve is oriented this way. We're going to want the tangent vector at that point here, which we're going to call r of u. And we're going to want a tangent vector for the curve, for the black curve, where we fixed v. We're going to call that r of v. Yep, okay. So at P, we have two tangent vectors. R of u and r of v. And since you want it to be at P, the u and the v that we plug into it are the ones from the point, u naught and v naught. So it's u naught, v naught, u naught, v naught. And so as you guys guessed it, we're going to want to use partials. We want to study the change of how the component functions of your vector function are going to change, but with respect this guy here, we're going to want to do it with respect. We want to see how x changes with respect to u. We want to see how y changes with respect to u. And then how z changes with respect to u. And that's going to give me that tangent vector right there, once I plug in u naught and v naught. And then we do the same thing for the other vector, but we're going to do it with respect to v changing. Partial of x with respect to v changing. So the same thing, but it's with respect to v this time. And then as you guys guessed it, we're going to take the cross product of this, and then that's going to give me the normal vector of that tangent plane to the surface there. So if S is a smooth curve, smooth surface, the tangent plane at P has the normal vector Ru of u naught v naught cross Rv of u naught v. So you guys had all the right ideas. It's just, it's all the computation part of how we're going to get that done. Okay. We're not going to focus too much on the tangent plane. Okay, we're not gonna focus too much. I just want to show you how you can derive it, because that tangent plane is gonna help us find the surface area of the surface okay? Let me see if I have the pictures. Let me open them up. Give me 1 second. In case you're writing that down. All right, this is section 16.6. All right, give me a second. Okay, so let me walk you through what we're gonna do. Okay. So this is what we found, okay? So what we're gonna wanna do is find the surface area of S. And as we've been doing all throughout the semester, to get that started is this vector function has a domain, okay? We're gonna break up the surface into small little parts by breaking up its domain into small little parts, okay? The intersection at each of these little parts, we're gonna pick a point on one of the corners there, okay? I can't draw on the board, dang it. But here, I'm not gonna draw on this, I'll get in trouble. You guys see this little surface area of this little piece right here? If I can get a tangent plane to that point there, so that the tangent plane is right above this small surface, so imagine like a small little tangent rectangular piece of paper there. The surface area of that small, dang it, I can't draw it, let me see. Let's see if I can go with this. You got that point right here, right? This is S of ij. There's a small tangent plane like this. That's the best I could do. Okay? There's a small little tangent plane piece there. The surface area, the area of that small tangent rectangular piece will be approximately the surface area of Sij. And the smaller I make them, the smaller I chop it up, the more the area of the small little tangent piece will approach the area of the small surface. That's kind of the gist of what we're going to do. Okay? All right, so let's see what can be done. Go away. All right, and so we're going to use this. So we use this to find the surface area of S. And so that's going to be our next task. Let's see how we're going to do that. To erase this long title. All right. So this little piece I drew here will be like some small little parallelogram, like that. Okay. Good review day today. So recall that if I have a parallelogram that's made by two vectors, throw back to chapter 12, right there. So area of parallelogram. Do you guys remember how we found the area? What equaled the area of the parallelogram? Cross product of the vectors? Just the cross product? cross product will be a vector, right? I want a number, so it's going to be the magnitude of the cross product of these two vectors. Okay, that was from chapter 12, little fact that we learned. And we're going to use that because that's going to help us find an area of these little parallelograms here. All right, so to find the area of S, we break it up into small pieces, as shown in the picture, Sij. As shown in your packet. I'm going to draw that and take over. So for each point Pij at Sij, which is the little corner point that your packet is showing you right here, the area of Sij, which your textbook is going to write delta Sij, is going to be approximately equal to the area of the small tangent parallelogram. The one I was trying to describe here. A lot of visuals today. So that little parallelogram, this is where it's going to get a little funky. Okay? You guys see the curve of intersection of P? That, like the one we just discussed for the tangent plane? There's a tangent vector, R of U, that's going to point this way. Okay? And then there's going to be another vector for the other curve. We're going to call that R of V, going the other way. But the magnitudes of those vectors will probably won't be what we want them to be. So we're going to do is we're going to scale them by the change of this delta U and delta V to give me that grid length that I want. Okay. So that little tangent parallelogram will be made up by these two vectors here, by scaling those tangent vectors. So I'll leave that picture here. And so since I'm finding the area of this tangent parallelogram, which is this green one here shown, that's what this is referring to. That means that delta Sij will be approximately equal to the magnitude of the cross product of those two vectors. Delta U RU star cross delta V RV star. Using this fact. In chapter 12, we also learned that if I do a scalar multiple of this vector A, so if I multiply that by C, I could take the C out, the absolute value of that C. So this is a scalar, this is a scalar. So I factor out the scalar, but then I also factor out the other scalar, which ends up giving me the product of those guys. Delta U, delta V. So this area of Sij will be approximately equal to this value here, which is supposed to represent the area of the small tangent parallelogram. And so what we're going to do is we're going to add up all those areas, all those Sijs. to give me the total area of my surface. And so we approximate the area of S by adding all these delta Sij's as we let delta U and delta V approach 0, meaning they're getting, you're breaking them up into even smaller and smaller pieces. And then once we do that, that's how we're going to get an integral in this case. But it's going to be a sum of two things, for U and for V. And so here's our first definition. If a smooth surface a smooth parametric surface S is given by R of UV and S is traversed, I'll explain this part, only once on its domain D that means for all the points UV that you plug in, you don't want two different points to give you the same output. Okay, like if you're drawing the surface, you want each pair of UV to give you a different different point on the surface. You don't want it to overlap. That's what this part says, which all the homework problems will have. Okay. The surface area of S is, it's going to be a double integral of all these sums here. So it's going to be the magnitude of RU, partial RU cross partial RV, dA. We kind of already knew how to do surface area back in chapter 15, but the only difference is that in chapter 15, you only knew how to find the surface area of a function, the surface of a function. So we couldn't do it for a whole sphere, for example, because that wasn't a function. Or a cone, remember the cone that goes kind of like the two-sided cone? You couldn't do the surface area. This is saying that you could do the surface area of any surface that's parametrized, whether it represents a function or not. So it's a little more powerful. Okay. So note, we can now find the surface area of surfaces that do not represent functions, z equals f of x, y. As long as it's parametrized, we can find its surface area now. All right, so I'm gonna have, I talked way too much. Let me have you guys try to find the surface area, okay? We did this surface last week. And now you're gonna find the surface area. So it says find the surface area of a piece of the cylinder given by R of UV is 2 cosine U, V, 2 sine U, where its domain includes only the points where U goes from 0 to pi over 2, and V goes from 0 to 3. We did this one last week. We looked at that surface, but now I want you to find the surface area. So notice you're going to need to know these partials. You're going to have to take the cross product, and then you're going to have to take the magnitude. That's the function you're going to integrate. Okay? So try it out. I see more folks showed up. You guys check in here. You two, and then I'll have you for the check out. And you guys have been- Try it out, see what you get. I have a couple more homework sets to pass back. So this is if you want to find a specific vector, but in this case, you're not going to want to find a specific vector. You just want to find a partial, because it's supposed to be a function, not like a point. Yeah, so you're going to find the partial of all three of these with respect to you. That's what you're going to call R. Then, that's more homework for you. Again, you're here. That does not sound right. Let me see. Here. Find the partials first. You're gonna want to find the partials. The partial of each of those. I believe I've only graded up to 22. Yeah. Let's see. Yeah, today we got 23 is due today. Yeah. 24 is due on Thursday. I accidentally put today. So, but it's supposed to be due. All right, guys. Some of you guys are kind of almost done. Some of you guys are kind of still in the beginning. Can I just have you guys check with your group mates? Check with your group mates, guys. Bounce off ideas. So do a quick check. Do a quick check. Real fast. See where you guys are at. That's a V. Oh shit. Oh shit. That's my bad. I'm so sorry. That's a U. Sorry, damn it. I'm sorry. I'm walking around I'm like, uh-oh. Okay. Sorry. I'm so sorry. Yeah, I'm so sorry. Otherwise you do not get a cylinder. My bad. Especially if you're using a pen. I'm so sorry. Yeah. My bad. I was just checking on the notes. I didn't know what they do. I know. I try to squiggle my U's as much as I could. So it goes like that. Hopefully make it easier. Oh, the first time. Yeah. You wrote it with a shit in it. There's other people who have completely different answers. I'm like, oh. But it was me. It's not you, it's me. So this is what you're finding the surface area of. It's like a piece of a cylinder where it only goes from 0 to pi over 2 for theta, or for your u. And then it goes from 0 to 3 for y. Ah. All right, you guys can check your answers here.
No, I
So you cross product is correct?
do get the one that.
Any other questions or look around? Good. Yeah. Yes. How's it looking like? You see your partials and your cross product is good? Yeah, and then things cancel out really nicely. This is it for 16.6. I broke it up into two pieces. First part was how to parameterize things, and then now we use that to help us find surface area. And so, like I said, we took a break from line integrals. We took a break from all that stuff from vector fields, right? But there's a reason we did this, because it's gonna all tie in together now. Okay? Now we're gonna put what we just did, parametrizing, surface area, all that, and we're gonna bring in vector fields back to the picture. Okay? Let's take a break. Take a break. We'll resume at not 2 o'clock, at 1:56. And then we're gonna do something called a flux. Yeah, which is we're gonna invent a new type of integral. It's your last one.
Use a lot of it.
Yeah, it's used a hell of a lot in physics. Yep. The way we're going to define orientation for a surface is we're going to say, are you on the purple side of the surface, on this side, or is it is it on the other side of the surface? We're going to use a normal vector for that. We're going to say, is the normal vector pointing in the direction that the purple side's on, or is the normal vector pointing in the direction of the yellow side? So a normal vector is what's going to tell us the orientation of the surface. Okay? We're going to start with that. And then we're going to figure out how to study the flow of the vector field across that surface. That's kind of the goal of what we're going to do. And as you can tell, it's going to be a little bit tedious, because there's all these different things that we have to define. Let's get this out of the way. And so I did hear some of you guys say that you've covered something called a flux in your physics classes. What were you guys using it for? Just curious. What were you studying in that class when you guys were using the flux? Physics. But what particular thing were you studying? So electricity? Okay. Anything else? Other folks? Electricity, magnetism, and then anything that you could think of like flowing. So there's also like heat. Okay, heat flows through particular things. So all those things are applications of all this. But as that video I showed you guys on YouTube, we're going to stick to the vector field representing like liquid and it flowing through something. Okay, so that's kind of how we're going to do it. But yes, it has applications for all kinds of things. 16.7. We're going to call it a surface integral, which is also referred to as the flux. So before we get to the flux, though, we have to talk about orientation. So let us begin by defining the orientation of a surface. Orientation of a surface. Something we have not done. To do all that, we need a surface as parametric. So for a parametric surface, S, given by your vector function, we saw that RU crossed with RV is a vector perpendicular to S at a point. Right, we just discussed that. So we define N to be the unit normal vector of S where we're going to say N is this vector here that you get of this cross product, but you want it to be a unit vector. So we just divide off its magnitude. So we divide off its magnitude. And so we get, you have your surface, you take the partials, you take the cross product, and then you're going to get a unit normal vector that's going to be perpendicular to the surface, okay? The direction that N is pointing can differ. N can point upwards, away from the surface this way, or it could also point downwards towards the xy plane, or however the surface is oriented, okay? But this bad boy is what we're going to be using. It can have two directions, right? Depending on the cross product that you end up getting, okay? So normally on the homework, they're going to specify the orientation they want you to use. Literally, they'll say, use the orientation so that your normal vector points upwards, or if the surface is sideways, it'll say the orientation points towards the y-axis. Like they'll really describe the direction they want you to use. Okay. You're then going to take this. You're going to find this normal vector, or actually, you're just going to find this guy, because this is the one that controls the direction. The bottom just divides it so that you have a unit vector. So you're going to find this cross product. When you're done, and we'll do it together. When we take the cross product, we're going to look at the result. You then have to stop and analyze the result of that cross product and make sense of it so that you agree with the direction that you're being told it should point to. And I'll show you guys how you're going to do it. Okay? But I just wanted to show you so that, there's two directions depending on the cross product. All right, so here's our first definition for this section. If S is a smooth surface so that at each point, there is a unit normal vector. n, and it can vary continuously. All these conditions, I apologize. So you have a surface, you have the unit normal vector just kind of continuously moving and flowing through, and it exists at all points on the surface. Then S is called an oriented surface. Asterisk here, with two possible orientations, like shown in the picture in your packet. All right, another picture in your packet. I won't go all the way down. Another picture in your packet. Our surfaces like spheres. Shoot. Our surfaces like this one here. I don't want to give this away yet. Like these two. Where they're going to be closed off. Okay? Closed off. We're going to define that in a little bit. So we're going to say a surface that's closed off will have outwards orientation so that the normal vectors are always pointing away from the surface, or it has inwards orientation so that the normal vectors are pointing in towards the surface. So again, we still have two orientations, but for a closed surface, there's an outwards and an inwards orientation. Okay? But first, another definition, because, you know, we're in a math class. We love definitions. All right. So if I was to tell my friend, oh, this is a closed surface, and I want to explain to them what that means, they're going to be a little lost. So we're going to say a closed surface. A surface is closed if it is the boundary of a solid. The boundary of a solid. And so like the picture of the sphere. The surface is bounding the ball, which is a solid, and it has outwards orientation, or it can have inwards orientation. That way, we can say, let's say it's heat. Is heat flowing away from the surface, the ball, or is the heat flowing in towards the ball? And that way we can use vectors to tell us the direction. Okay? Jacob.
So I just want to verify that outward orientation is the same as positive orientation and negative orientation is negative?
No, that's different. So that's probably what I'm going to do at the review. There's so many different definitions that next Tuesday we're going to review the vocab, because now there are things that there are curves that are positively oriented, and now there's going to be surfaces that are positively oriented. Okay. We haven't gone there yet though, with the positive orientation. Okay. But when we have outwards orientation, your textbook is going to call that a solid that has positive orientation. Okay, and if it has inwards orientation, it's going to have negative orientation. Well, but this is only for closed solids. That's what's a little confusing. So that's part of what I'm going to do on next week. We're going to review vocab. So that's going to be key for the theorems that you're going to have to use. Okay? Okay. So we have what we need now. So we have a way of defining orientation of a surface given this unit normal vector. And then for a closed surface, we have new vocab, which is outward orientation or inward orientation, positive or negative. And we know what a closed surface is. So now we have the vocab and the tools to help us construct the flux. Okay? So we can now learn how to determine how much a vector field F flows through an oriented surface S. We're bringing in vector fields now. So to help, imagine F represents liquid flow. Just to kind of help you grasp this, because it's very abstract. Imagine F represents liquid flow, and S is a thin net, a very thin net, the surface, okay? It's a very thin net. We would like to measure the flow rate of liquid through S. How much liquid is flowing through S per unit of time? Per unit of time. We call this flow rate the flux of F across S. Through that picture that I was showing you guys earlier. Okay? That flow that's going through it. As usual, in class I try to show you guys some construction of these things, right? This one's heavy, so I'm just going to show you the construction. I'll put it in my notes, but I want to move on because the problems with these take hella long. So I want to focus on examples, okay? But I will show you the construction. So let me give you the definition first, so that it's in your notes, and then I'll explain the construction of the definition. But I don't need you guys to take notes for it. I just want to show you how we get this definition. All right, so this is how we're going to define it. We're going to say let F be a continuous vector field defined on an oriented surface. And what I mean by that is every point that lies on the surface, I can plug it into the vector field to give me a vector. That's what that means, okay? On an oriented surface S with unit normal vector n parametrized, big old definition, by R of UV. Whew, let me stop that. There's a little bit more, but slow down. So we have a continuous vector field so that any point on the surface, you plug it into F, it'll give you a vector. And that S is oriented with some unit normal vector n, and it's parameterized by R. Right? If D is the domain of your vector function, the domain of R, we're going to say the surface integral, which is also referred to as the flux of F cross S, is defined as, so you remember how a line integral, we went like this for a line integral? This time we're going to do two integral symbols, and we're going to put the surface on the bottom. Of F, let me write this, you don't write this part. Remember how we did this for a line integral? Does that kind of look familiar? So the surface integral is going to be a double surface, double integral here, symbol, over S of F dotted with something called ds, which is what I'm going to show you guys what that means. The way we define the surface, the line integral, I just want to show you guys the similarities, okay? You don't have to write the blue part. This is how you did it by definition. Does that look familiar? So for a surface integral, this is a vector field in a vector field here, and then this is R of UV. It's going to be defined as the double integral over the domain of your function of F composed with R of UV dotted with the cross product of the partials, dn. So notice some similarities with a surface integral and a line integral. You're integrating over the domain of R. The domain for a line integral is where t varies from a to b. You're composing the vector function into the vector field, and you're dotting it with its derivative. Or here, this is considered the R prime version. Okay? And so we're going to have to construct a double integral, which is the chapter 15 integral. All right, let me walk you through the construction. You do not need to take notes of it. I just want to show you. If you want, the notes will be posted for it. Okay? I just want to walk you through the construction. So I cannot show you that. It's like the math in me would kill me. Mathematician in me here. Okay. So here's an explanation of kind of how this ends up working out. All right, so you have some parameterized surface that is oriented by n. You're going to get your surface, as we did before. You're gonna get your surface. You're gonna break it up into small little pieces, okay? Which are gonna be approximately small rectangular pieces, like what we did for the surface area. And then what we're gonna do is we're gonna determine the flux on each of these small little rectangular pieces only. So we're gonna only focus on one of these pieces. Okay? Think of it as this picture that I have here. So you're gonna get only one of those pieces, and you're gonna look at the flow of the vector field in only one of those pieces. Those pieces are gonna be very small though, okay? They're like really, really small. So then that means that all the vectors that flow through that surface are gonna be practically the same because you're not varying the points as much. Like they're all gonna be pointing relatively in the same direction, and they're all gonna relatively have the same magnitude. So think of water flowing through that little piece. One of these little guys. Okay? Where the blue vector is the orientation vector. That's the unit normal vector. And the red vector is what you get when you plug in a point from the surface into the vector field to give you the vector. Okay? So take one of those pieces, consider some rectangular surface S given by R of uv that is oriented by n. Let's say it's this little piece here. We're only going to focus on one of them. Okay? You got your unit normal vector n, which is a unit vector. We're going to define where this guy comes in. Okay? We're going to define a mu vector called delta S, which is the unit normal vector scaled by the surface area of that small little piece, delta S. Okay, so we're going to stretch it so that it equals the surface area of that little piece. Therefore, this new vector, the magnitude of it, is the magnitude of this guy here, the scalar multiplication, which is the area of S times the magnitude of n, which is 1. So that means that all these delta S vectors, their magnitude is the area of that little s. Okay? So it's like a little trick that we're doing. We're creating a vector so that its magnitude equals the area of that little small rectangular surface. Okay? And so that it's also parallel to your unit vector. Okay? Nice little trick there. Okay, so then we get a point on the surface and we plug it into the vector field to give you this vector here, pointing in whatever direction it's pointing, however it's flowing through us. Okay? As I mentioned, since S is very small, I do that for all the points on the surface, and because that surface is so small, all these points are practically very close to each other. So all the vectors will be approximately the same magnitude, and they'll be approximately pointing in the same direction. Because we're varying that point very little bit, since you're only looking at a really small piece of your surface. And all the vectors here will flow relatively in the same direction and have relatively the same magnitude, versus if I'm over here, maybe now they're going this way. Okay? You guys see this, like, I forgot what it's called, it's like a fancy name, parallel pipette or whatever, but you guys see this slanted box? Okay? The volume of that box is going to give us that flow of liquid, the volume of the liquid flowing through it at a unit of time. Okay? So we want to find the volume of this little box, which you guys can think of as all these infinite vectors that are flowing through it. The amount of liquid flowing through it. Okay? So to find the volume of it, we're going to need the height of it. So you have your delta S vector, which we know is perpendicular to the surface, since it's parallel to this guy. And we defined it to be perpendicular to the surface, and then you have this orange vector, which is the vector field vector. Its magnitude is that length. So then the height is, you use a little bit of trig with cosine here. Cosine of this angle is h over this. And that gives me my height in terms of the magnitude of that vector field. Okay? So we get that. Where's my fancy ruler? What I put? You guys see where I put the ruler? Oh, okay. So here's where everything starts to collide. Okay, so my goal is to find the volume of that box, which represents the amount of volume of liquid flowing through here. So that is approximately going to be the area of my base, which is the area of S, times the height. The area of S, we're going to define it to be the magnitude of this delta S vector. Okay? The height was given through the magnitude of F cosine theta. And so then chapter 12 comes in and says, look, this is the product of the magnitude of two vectors times cosine theta. So then remember from chapter 12, the dot product theorem, that is equal to the dot product of those two vectors. Okay? But this vector delta S, we defined it to be the area of S times the unit normal vector. And so then we bring in the other stuff. Well, the n vector, we defined it to be this guy here, the magnitude of the cross product over the cross product. That's n. And then from section 16.6, we saw that delta S was the magnitude of this cross product vector times delta V. This is from 16.6. So then at a particular point, you got this little rectangular piece there. That point is given by some u and some v. And so that point which I plugged in to get f is given by what I get when I plug u and v into R. Okay? That's where the composition comes in. Because this composition is, think of it as like the points that you're plugging into the vector field to give you all those vector fields from the surface. Then you got your delta S right here. That delta S is this bad boy times n, which is this bad boy right here. And so beautifully enough, these end up canceling. Okay? And so then we end up with this result here for just that small little rectangular piece. Add all those up as delta V and delta U go to 0, and that's what produces this result right here. But this is the way we're defining it. It's like the notation we use. I'm not going to expect you guys to know. I just wanted to show you the construction of it because we're in a math class and that's what we did. All right, some gnarly stuff. Okay, so what I want to do is I want us to get started on some examples with these flux surface integrals so that you guys can see how fun they are. And because I've been talking way too much. All right, so let's see. How are we going to do this? I'll do an example, and then I'm going to have you guys try one. All right, so this is like something you'll see in your homework. It says find the flux of F x, y, z which we're going to use the vector field is not too gnarly. It's just x, y, 5, x comma y comma 5. We want to see how it flows across the cylinder the same one you guys just did before the break, that little piece of the cylinder, S given by R of UV, 2 cosine U, this time I'll write it correctly, 2 sin U, so 2 cosine U, comma V, 2 sin U, with the same domain that I gave you guys last time. So U will vary from 0 to pi over 2, and V will go from 0 to 3. And then the textbook will say this: let S have downwards orientation towards the y-axis. So we've been playing with this surface a lot from the beginning of 16.6. It's that same one that I've been showing you. It's a cylinder that goes from 0 to pi over 2, and it only goes up to y equals 3. So it's this piece here. Okay. But notice the orientation that they described to you. It goes like inwards, yeah, it's going towards the y-axis. So your normal vectors need to be pointing this way. Your unit normal vectors. That's that last part. Okay. Remember on the warm-up, sorry, on the problem set, I had you guys do a problem last week where you basically had to conclude if the line integral would be a positive answer or a negative answer based on the orientation of the vector field and the curve. You guys remember that problem set last week? Okay. Hopefully you did. If you do a line integral and you get a negative answer, what did you conclude visually is happening? The vector field and the direction of the curve are going against each other most of the time, right? If you get a positive answer, the vector field and the curve are most of the time flowing with each other towards the same direction, relatively, right? So here, when you do a flux, if you get a negative answer, what do you think that means visually for this example? Let me have you guys discuss that real quick with your groups, because that's important, especially if you're doing it in physics. So if you get a negative answer versus a positive answer, what does that tell you about this whole thing we're discussing? Yeah, if we end up doing this, what does it mean if you get a negative answer versus a positive answer? How is your liquid flowing through the surface? Depending on the answer. Please discuss it. In case I have you guys share out, discuss it with your classmates. This is an important part conceptually of this. All right, let me hear from this side of the room. If you get a negative answer, what does it tell you about how the vector field flows through S? Okay. Someone from this side. These three rows. Okay. Use yourselves. If it's negative, it's negative.
Negative, then the normal vectors overall point in the opposite direction from the vector field more than the two vector.
Okay, so it would be like the vector field is flowing most of the time flowing this way. If you got a negative answer. And if you get a positive answer, how is the vector field flowing? Then it's it's pointing in the same direction, most of the time, as you said. So it's flowing in the direction of N. Right? So that's how you're going to use this answer to kind of give you an idea of what's happening. Okay? So if it's positive, so F flows against N, which is the orientation. But if it's negative, F flows, let's put mostly towards N. Okay, good. All right, so let's see how we're going to do this. So we need a couple things. We need the partials. We need the cross product, like you guys did for surface area. So let's go ahead and do that to begin this problem. So I'm going to need to take the partial view of my vector function. Okay, partial view. That's the same thing you guys did earlier. You guys get -2 sine u, 0, and 2 cosine. Okay, that's the partial view. Partial v, just like you guys got last time, u is a constant now, so it's 0, 1, 0. 0, 1, 0. So then you take the cross product. Let's see, ignore the first column. So you get 0 minus the product of that. So you get -2 cosine u. Middle one, you always negate it. Cross off the middle column. 0 times 0 for both, so it's a 0. And then cross off the third column. The product of these two, which is -2 sine u, minus the product of these zeros. So that's just 0. Is that what you guys got? For the last? It's the same cross product that you guys did in the last example. Okay. That is what we're going to be using here. Okay? Now we need to do this part. We need to do the composition. That's where it gets tricky. Okay? So let's see. So I got that piece. R of uv is 2 cosine u, v 2 sine u. So this is my x, this is my y, and this is my z. That means when I plug it into my vector field, the x gets replaced with the x function, which is 2 cosine u. The y gets replaced with the y function, which is just a v. And then the z component is just a 5, so that's just stays 5. All right, so now I have the two pieces I need. So therefore, now we can find this flux here. That's going to be the surface integral of f dot ds, which is the double integral over my domain that I'm given. Of f composed with u, or sorry, r of uv, dotted with the cross product. I'm just doing the definition again. Oh, I forgot an important step that I told you guys you need to do, and I didn't do it. Okay, hold on, let me stop. This part right here. We need to guarantee that n is actually behaving the way we want it to. N is parallel to this guy here. Right? Those are parallel vectors. N is just this guy, but divided by 10. So I took the cross product here, and this is what I got. Okay. How can I tell from what I have here that it's actually pointing in the way that I'm asked it should be pointing? No.
The higher to cosines are positive, so you have to put this value.
Correct.
And cosine,
Positive or negative? Cosine is always positive, so you'll know the component is always negative.
and same thing for sine,
And the same thing for sine.
so those are going to both be negative.
So these two components, x and y, are always going to be negative. Think of vectors now. What does that mean? That means that if I have a vector, here, I want x to be going in the negative direction, so it needs to go this way. And I want z to go in the downwards direction, so it needs to go down. So notice that will force the vector to do something like that. So anywhere here, x will always have to be negative, so that will guarantee that it's pointing this way. And if I'm up here, z will always be negative, so that's going to guarantee that it's pointing that way. You guys kind of see that? That part's hard conceptually, okay? That's the part that's going to be like a little funky. Why do I care about that? Because if I do the cross product and I don't get that, let's say I would have gotten this, and I do all my work, I'm going to end up with an answer that has the opposite sign of what I'm supposed to really have. Okay?
So just put a negative sign.
So you smack a negative in front of it. Same as when you did with curves and oriented curves that were not positively oriented, you just negated the answer. It's the same exact idea here. Okay? So let's write that down. So if this vector points in the opposite direction, then negate your final answer. And so if you do a homework problem and then later on you check the answer and then your answer is negative, but it's giving you that it should be positive, go back, check your cross product, and see if it aligns with the orientation the homework problem has to do. You do need to use the bounds to kind of see, so it's a little bit of knowledge of functions to kind of understand the values of them and what you actually have here to see if it's going to give you what you want. Okay. Okay, where were we? Okay, so here we go. So I have my double integral. This vector here is what we got with this composition. So it's 2 cosine u v5 dotted with the cross product, which is minus 2 cosine u 0 negative 2 sine. VA. And then let's paste. Actually, let me do this in each case if you guys have time. We've got canceled out. Yeah. So the surface area uses magnitude. A surface integral does not use magnitude. Yeah. Nice observation. Okay. Let's see, guys. Help me out here. So this would be that minus cosine squared u, and then plus 0, and then minus 10 sine u. So we end up with, let's see. We end up with minus 4 cosine squared u minus 10 sine u. Okay, let's do the bounds now. The domain describes the bounds of D. It's already giving you the bounds here. Okay. So do you guys want to do it with respect to U first or with respect to V first? You'll eventually be able to separate it. No, you won't. Let's see. U goes from 0 to, what did we say? 5/2. And then V goes from 0 to 3. So we're going to do du first and dv second. Okay. The reason I can't separate it is because this is not a product of u's and v's. Oh wait, it's just u's. We can't separate it. Sorry. We can separate it into an integral with just v's and an integral with just u's. Yeah, you're right. So then that's going to be an integral with just v's, which is just 1, and then an integral with u's. Cosine squared u minus 10 sine u. I do the entire work on the notes, but here we're going to skip it. Here you're going to get 3. And then here you're going to get, let's see what I'm doing. Minus pi minus 10. Which ends up being minus 3 pi plus 10. And then if you put that in decimal form, that's about negative 39.4. Let's skip a couple steps here, just to not do the entire integration. You gotta use double angle or half angle formula and all that good stuff. Okay. But if you work this out, this will be your final result. And it's negative. So what does that tell us? If it's negative? Going more or less against, it's going to go against the vector field, the surface, this way. Sorry. You don't, because remember when the construction that I was showing you guys, those things canceled out? That's the beauty of that.
The Flux is not, it's like functional. There's a phase, the same time, like how many flux?
Yeah, if this was liquid, let's say whatever units, this would be this many units cubed per unit of time. Okay. The absolute value of it would be that amount of liquid. That's units cubed per unit of time, whatever the units is on the application time. But this is telling you how much, the absolute value of it tells you how much is flowing, that flow rate, but the negative tells you the direction at which it's flowing. It's flowing opposite of the orientation of S. Let's confirm it. Oh, Charlie, sorry. Yeah. We won't have much time for applications because these problems take a really long time. Okay? Yeah, they take a really long time. Oh, I reset everything. Yay. Okay, let me see. Hold on. Let me do this real fast. All right. Vector field. So it was x, y, 5, right? Okay. So this is the vector field. Like this. And now let me put it away. And then let's do the surface. It was 2 cosine u, right? V 2 sine u. And u went from 0 to pi over 2. And v went from 0 to 3. Okay. Let's do 4, 4, 4. This is a little more fancier than GeoGebra and Desmos. Okay, so here's the surface. It was pointing downwards. And this is the flow of the vector field. It's pointing, as we imagined, opposite of the orientation. Okay, so we guessed it correctly. And it's doing it a lot, which is why we got such a big negative number. There's a lot of flow happening through it. This is scaling the vectors, but they're really this long. Okay, it's just messy and ugly. But that's why that negative was so big. Okay. Before I move on, questions on this guy here? Sure? You ready to do one on your own? Yeah, there we go. Okay. Actually, I'm going to give you another really helpful tool, okay, before I have you do one on your own, which you're going to love. So in this case, our surface was given by a vector function, right? If your surface is given by a function, okay? So here's a nice tool. If your surface S is a surface of a function z equals f of xy, like what we did in chapter 14, with domain D, there's a nice shortcut for a vector field given by P, Q, and R. It turns out that if I want to do the flux across that surface, there's a nice formula for it, where it's the double integral over D of negative P, which is this P, times the partial of F with respect to X, minus Q times the partial of F with respect to Y, plus R. And so the shortcut is that basically it gives you the final function. And it has you not have to do all this. That's the shortcut. It'll give you, once you figure that out, it'll give you the function that you're going to integrate. Okay. That's times. Yeah, that's times. Okay. When you do this formula assumes upwards orientation. Since it's a function of, it represents a function. Okay? So it assumes that your surface, which is the surface of a function now, it's going to assume, whenever you use this formula, that your n needs to point this way, upwards. However, this thing is a curve. Okay? But if it doesn't, exactly, if it doesn't, then you do this here. Okay. So I don't want to erase any of this stuff here. I'm gonna squish it right here. So that you guys can use some of this if you need to. All right, so here, I want you guys to try one. Find the flux of F given by YXZ across the surface S that is the paraboloid z equals 1 minus x squared minus y squared above the xy plane. So notice the difference of this problem is that it did not give you the parametrization for it. Okay, it gave you the equation for it. So either do it like this, or see if you can use this. Okay. Try that guy out. I'll tell you now, all these problems are going to take a lot of time. Okay, so that's why the homework is not as crazy long. Yes. If you couldn't use that, then you would have to create your own parametrization, which are the type of homework problems at the end, where you have to create your own parametrization. Yeah. Say that one more time. It would then you need to know if you can't use this, then you have to create an R, so that you would then do this and then do this. Yeah. Mm-hmm. Let me point something out, guys. You see this Z right here? See that Z? That Z can be replaced by whatever the function is. So that means that my Z here can be replaced by all this here. Your integral, you want it to be only of two variables. You don't want x, y's, and z's here. You want it only with two variables because it's a double integral. Okay? Correct. Yeah, these are the P, Q's, and R in this case. P, Q, and R. Correct. Yeah. Above the XY plane, so it's like chapter 15. So we did chapter 15. Yeah. Above the XY plane, guys, so it's a paraboloid above the XY plane. So you need to figure out, like you guys did in chapter 15, you need to figure out what are the bounds, what is D? What's the domain? So it's very chapter 15. You will eventually look. Yeah, I'll draw a picture for you guys. This is D right there. I'm reminding you of chapter 15, okay? This is the paraboloid. That's S, right? Above the XY plane. But when you construct the double integral, that's D, like you did in chapter 15. You gotta figure out on the XY plane, what's the domain on the XY plane for the paraboloid. Bring all that up.
You want the normal vector plane.
If you're going to use this guy, you assume it's upwards orientation. Yeah, this formula, the way it's constructed, it assumes that endpoint's upwards. Since this, if you use this tool, yeah, then yes.
Because he didn't say it.
Correct. Let me see how the textbook would have said. Give me a second. Shit. Let's see. The textbook, I believe it would have said something like that. Oh, you're right. I forgot to write it. I forgot to write that it's supposed to say this. It has upward orientation, guys, okay? Yeah, I forgot to write that part. What? Yeah, 4? Let's see what's there. Ooh, that's not the domain. Yeah, because there is an XY plane. On the XY plane, your domain looks like this.
Otherwise,
Which is not, shouldn't be a square.
you use cylindrical.
Yes. Because it's a source. I know you hate when I put you together, but it's fun. You guys are having a hard time. All four of you guys, group up, check in with each other. You two here are working really well. You guys. It's a circle. Might not have I think it means that. Yeah, that's because the partial Well, so your parabola, right? It is a circle. How did you figure out the radius of the circle?
Well, it's a negative parabola, it's shifted out by 1, so that the radius would have to see the xy plane for the line, because it's just.
Yeah, you can also let the equation that z equals 0 and another z equals 2. So when you guys did this in chapter 15. When you guys did it in chapter 15, you kind of circle radius 1 as your domain. You switch the polar. Remember the way you switch the polar. So R starts from the origin, you have what's the biggest stretch? Which is 1. So what's the smallest stretch? 0. That's your bound shape. And the theta was what the little bit of the laser is. So 0 all the way to
I saw Fiber two. As an expert, so I tried it. I found my. Yeah. Just very.
I understand now the condition of everything you have on both sides, and I'm actually determine the with two sign data. Oh, that's two. That's one. Oh, you mean like
So you have to convert this one into cylindrical spherical. You can't do it.
You don't have to, but your bounds are gonna be pretty low.
I thought that was the bound. That's just like going like that.
So you see this, you see the paraboloid right here? It's a paraboloid, right? Chapter 15, go back to chapter 15. And you're doing a double integral of a paraboloid of what? So you want to figure out on the xy plane that circle of intersection. And so you let, on the xy plane, you let this equal 0, z equals 0 on the xy plane. So then you get that on the xy plane, which is a circle of radius 1.
Much easier doing it that way.
Yeah, so that tells you that on the xy plane, all the points that are being plugged in come from that circle here. And so that's why folks are converting it to polar. Okay? Let me just show this. These people need to. All right, guys, hopefully you got something that looks a little like this. Can I make it? Oh, damn. So just a recap. Where's my fancy ruler? I'll use this piece of stick. So your R here, your R is just Z, but like as I mentioned here, all the Z's will be replaced with the function itself. Okay? And so they get replaced with the function, so then that's where that R ends up being the function itself. You multiply these two products, you get this. The bounds, I think, is what's tripping up some of you guys, is you got to go back to chapter 15. I know it's been like a long time, but when you're double integrating this paraboloid above the xy plane, you set the paraboloids where z is equal to 0, and notice that tells you it's a circle of radius 1. That's the domain of your function. Only points from that circle are being plugged in to give you your parabola. So because the domain is a circle of radius 1, you can convert to polar if you would like. It's the easier way to go. And so once everything gets converted to polar, these will be your bounds. All the x's and y's get replaced with sine and cosine, and then blah, 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 blah. Integration. Okay? All right. Good job, guys. We got 3:15, perfect timing. All right, flux time.